Hello, all students in Section 5, Section 6. Take note that this is not a replacement lecture, but more like a supplementary materials for the lectures that are to resume when UTM reopens. However, today I have been informed that there is a possibility that starting 1st of April, teaching and learning will be done online. But meanwhile, let's have a look at the lecture materials that we are supposed to learn last week, convection. So this lecture is on fundamental concepts of convection, Newton's law of cooling, which you have been introduced to during the first week of the semester. So this lecture will cover convection mechanism and dimensionless parameters. All of you have been introduced to the velocity boundary layers for the laminar and turbulent flow conditions, as well as the very important Reynolds number. In heat transfer, you'll be introduced to another type of boundary layer, the thermal boundary layer, and two very important dimensionless parameters, the Prandtl and Nusselt numbers. Now, how does convection happen? Convection happens due to two mechanisms, which are random molecular diffusion, involves collisions between molecules, and macroscopic bulk motion. We will have a look at both of these in this particular topic, convection heat transfer. As you have been told during the first week of the semester, convection is one of the modes of heat transfer besides conduction and radiation. And you have been reminded that this particular class, we will look at convection between a moving fluid and a solid wall. In conduction, you are all most particular about the temperature profiles within the solid or stationary fluid, as well as the heat transfer involved. In convection, however, almost every time we are interested in the accuracy of obtaining the convective heat transfer coefficient H. Okay, before H is given as a constant value, but in this topic we'll look at how H varies, whether your convection is forced, that means require external forces like a fan or a pump, and forced convection, there are two types, external flow and internal flow. The second type of convection is natural or free convection, which does not need any external forces like a fan or a pump, and only occurs in external flow. Let's have a look at Newton's law of cooling for now. You have here equation 6.1 and 6.2 in your Chengel textbook. The rate of convection heat transfer is given by Newton's law of cooling. Let's say if you have a particular solid wall at a constant temperature Ts, and there's a fluid moving over it at the temperature T infinity, if there is a temperature difference, there would surely be heat transfer from or to the wall. So, for this particular case, with the constant temperature along the wall, you can determine the heat flux or the heat transfer from the wall or to the wall if you know H and knowing the Ts and T infinity. Okay. The accuracy of the value of heat transfer is actually determined by the H correlation. Yes. So this convective heat transfer coefficient H is the rate of heat transfer between a solid surface and a fluid surface per unit of surface area per unit temperature difference. Hence you can see the unit is watt per meter squared per Kelvin. Now, by the description of H, how would the rate of heat transfer by convection be affected? Let's have a look. Here a summary of what factors affect the H. See, most importantly, whether it's internal versus external flow. Earlier I mentioned that for natural convection, there is only external flow. So for forced convection, you would have to determine whether your flow is internal or external, whether your fluid is viscous or inviscid. And of course, only ideal fluids have zero viscosity, but most of the time we like to assume that our gaseous fluid is inviscid. And we have to use Reynolds number to determine whether our flow is laminar or turbulent, steady or unsteady, one-dimensional or multi-dimensional, compressible versus incompressible. Zero viscosity means there are no frictional effects between the fluid flowing to a solid wall. There is no slip. Sorry, there is a free slip. And between fluid layer and fluid level. Internal flows involve fluid flow in confined spaces, and if there are some free surface above the duct flow, it is considered open channel flow, which we will not cover in this course. Incompressible flow occurs when the density remains constant. Liquid flow is typically incompressible, while that of gas flow may be considered as incompressible if the density changes is less or equal to 5%. Smooth and orderly fluid motion constitute a laminar flow, while that of highly chaotic fluctuations is turbulent. And this we can determine through the value of Reynolds number. Okay. Remember that for external flow, generally we take about 2,300 Reynolds number as the separation between laminar and turbulent. And for internal, we will look at it later on in the course. So forced flow occurs when the fluid motion is initiated by external means, fan, pump, etc. While natural free flow happens when buoyancy effects generate fluid motion due to heat transfer when warmer fluid rises, because warmer fluid is lighter and being replaced by cooler fluid, and thus a motion is initiated, the cooler fluid replacing the warmer fluid that rises. Steady flow means no change at a point in time. Uniform means no change with location. Take note of that difference between steady and uniform. 3 and 2-dimensional flow can often be treated as one-dimensional if there is symmetry of negligible effects in the other directions. In this course, this SKMM3443, Section 5, Section 6, we will be looking only at effects one-dimensional steady-state flow conditions on force and free convection. The effects are represented in the H correlation that you select to determine heat transfer, and there are many. Yeah. Velocity boundary layer, which always exists whenever there is a fluid flow next to a solid surface. Always, any particular surface is always next to a fluid, we have velocity boundary layer. The fluid particles next to a solid surface have zero velocity, yes, that, no slip, and they retard the molecular motion of the adjacent fluid layer, which in turn retard the motion of the next fluid, and so on and so forth. Yeah, see, we have a leading edge, and the direction of X is here. This is the thickness of the boundary layer. The retardation of motion continues until at the distance of y is equal to delta from the solid surface, the effects becomes negligible. So this is delta. So the effects of the viscosity will become negligible with y, and it will be as a free stream velocity. It reaches free stream. The retardation of motion is due to the shear stresses acting planes parallel to the fluid velocity due to viscosity. Yes, you have learned that in your fluids. With increasing distance from the solid surface, the x velocity component of the fluid U must increase until it approaches the free stream velocity. So this is the x component velocity. Yes, it will increase from 0 because of no slip condition. It will increase until it reaches the free stream velocity at the boundary of the velocity boundary layer. Now, within the boundary layer, velocity gradients and shear stresses are large. Yes, within this boundary layer, the velocity gradient is large. The velocity boundary layer is also known as a hydrodynamic boundary layer or just plain boundary layer. So when you hear boundary layer, it is generally referring to the velocity boundary layer or the hydrodynamic boundary layer. It involves surface frictional effects. For external flows, the velocity boundary layer is the basis for determining the local friction coefficient, skin friction coefficient, which I've learned again in your fluid last year. It's a dimensionless parameter from which the surface frictional drag may be determined, and the friction force over the entire surface is determined from 611. If the fluid is assumed Newtonian, which we always do in this class, the surface shear stress, tegasan receh in Malay, may be evaluated from this equation using the dynamic viscosity. There are other non-Newtonian fluid. Blood is one example. Is your blood. It doesn't follow the Newtonian law. It is actually following the, is model as a power law. Yeah, that's why I'm going to tell you about non-Newtonian fluid in this class. Yeah. The thermal boundary layer. Now, the thermal boundary layer, unlike the velocity boundary layer, it only exists when there is a temperature difference between the fluid and the solid surface. If there is no temperature difference between the solid and the neighboring fluid, there is no thermal boundary layer. There is always velocity boundary layer. So at the leading edge, the temperature profile is uniform, as you can see here. Yes. A temperature gradient soon develops when the fluid molecules next to the solid surface attain thermal equilibrium with that surface. These particles in turn exchange energy with the next layer of fluid particles, as you can see here. See, assuming this is at Ts, constant isothermal temperature on the solid wall, and you have an approaching fluid at T infinity. In this particular example, let's say Ts is much higher than T infinity, and you would expect heat transfer from the surface to the fluid. Yes. So you have a temperature gradient, which is heat transfer from the molecules next to the solid to the neighboring fluid layer. As you can see here, the temperature profile is decreasing up to the free stream temperature. And this thickness is called thermal boundary layer with the subscript T. Previously, it was velocity boundary layer or hydrodynamic boundary layer or just plain boundary layer. Yes. So now, the region where the temperature gradient exists is the thermal boundary layer, typically defined as the value of Y for which this quantity. Okay. The thermal boundary layer thickens with distance from the leading edge, just as the velocity boundary layer also thickens from the leading edge. Yeah. Okay, let's have a look at how the convective heat transfer coefficient decreases from the leading edge. See, so you have pure conduction at the interface between the solid and the fluid, the adjacent fluid, as have been discussed in earlier chapters. Yes. If you do energy balance on that, you would have that the conduction given by Fourier's law, and that would have equal to the Newton's law of cooling. If you substitute the Q, you would have this equation. Yes, there's a Newton's law of cooling for heat transfer from the surface and the Fourier's law of conduction in the solid wall. So there is no fluid motion next to the surface, yeah, and energy transfer occurs only through conduction. Now, if you look at it, the example was shown earlier here. We imagine this is an isothermal condition at Ts on the solid wall. So this would be a constant, the denominator. Yeah. But as the thermal boundary layer increases with x, yes, the thermal boundary layer is increasing with x, the horizontal distance. So the temperature gradient dt dy must decrease with increasing x. See, the dt dy here is large, it is decreasing with x.